Hello everyone, we are going to discuss question number 44 from MTP3. So here we have to calculate the millimeters of 0.5 molar H2SO4, that means volume of 0.5 molar H2SO4 which is needed to dissolve 0.5 gram of copper carbonate. So coming to the solution part, we will write down the reaction between these two. This will come out to be CuCO3 plus H2SO4 and the products will be CuSO4 plus water plus CO2. As we know that both are taking part in the reaction, so both will be having the number of millimoles equal. We can calculate the number of millimoles of copper carbonate. That will come out to be 0.5, that means its mass divided by its molecular mass, that is 123.5 multiplied by 1000. So millimoles of copper carbonate is 4.048. Now that means that we need 4.048 millimoles of H2SO4 as well for the reaction, and number of millimoles is given by molarity multiplied by volume in milliliter. So volume in ml will be equal to number of millimoles divided by molarity. So substituting these two values, we will get 4.048 divided by 0.5. So the volume in milliliters that is required will be 8.096 milliliter. Hello everyone, we are going to discuss question number 45 from MTP3. Here we are given that the absorbance maximum is 0.9, that is at 510 nanometer wavelength, and the spectrum is recorded on a solution having 0.2 molarity and the cell length is 1 centimeter. So we have to calculate the value of epsilon at this wavelength. Now here we will use Beer-Lambert law. According to Beer-Lambert law, A is given as absorbance is given as epsilon into C into cell length. So we have to find out the value of epsilon. So epsilon will be given as A divided by concentration of the solution multiplied by cell length. After substituting all the values, we will get it as 0.9 divided by 0.2 multiplied by 1 centimeter. So the value of epsilon will be equal to 4.5 centimeter inverse molar inverse. Hello everyone, we are going to discuss question number 46 from MTP3. Here we have to calculate the lattice energy of a salt from the data that have been given in the question itself. Here in this kind of problems we have to apply Hess's law. According to this law, enthalpy change for any particular reaction is similar or constant irrespective of the path that have been followed. That means the heat of formation for the process will be equal to the sum of heats that have been either released or absorbed in the minor steps. So we will start with the metal, as we know that metal exists as solid in nature. So first of all, we have to provide heat of sublimation in order to change its phase from solid to gaseous. Now we have to further give some energy in order to ionize the metal. That energy is ionization energy. Now the metal is in form of M+. Now coming to the gaseous molecule part, first of all we have to provide the heat of dissociation in order to convert the molecule into atom. The heat of dissociation, if it's D, then we have to provide D by 2 energy, as we need only one atom of X. Further, when we add one electron, then energy will be released, that is known as electron affinity. And the final step is when both the ions are brought together, then the energy will be released, which is known as lattice energy. Now, combining all the energies that have been covered in the following steps, we will write as sublimation energy plus ionization energy plus bond dissociation energy divided by 2 plus electron affinity plus lattice energy, and the sum of all these energies will give delta H. Substituting all the values that have been given in the question, we will get U, that is lattice energy, is minus 738.5 kilojoule per mole. Hello everyone, we are going to discuss question number 53 from MTP3. Here, bond energy of CH bond and O double bond O, C double bond O and C single bond C are given to us, and we have to find out the enthalpy of combustion of butane in kilojoule per mole. Let's go to the solution part. First of all, we will write down the reaction of combustion of butane, and the reaction will be C4H10 plus 13 by 2O2, and the products will be 4CO2 plus 5H2O. Now, in the reactant sides, we have to provide energy in order to break the bonds. So the energy that we have to provide will be equal to the energy to break CH bonds. There are 10 CH bonds, so we have to provide 10 into energy for 1 CH bond, plus there are 3 C single bond C, so we have to provide 3 times energy of C single bond C, plus there are 13 by 2 O2 molecules, that means 13 by 2 O double bond O, so we have to provide that much of energy in order to break those bonds. After substituting the values from the question, we will get the energy that we have to supply in order to break the bonds in reactant side as 8387 kilojoule. Now coming to the product side, as we know that bonds will be formed, so the energy will be released. Now first of all, we will look for the energy that will be released in the formation of 4 moles of CO2. As we know that 1 mole of CO2 has 2 C double bond O, so 4 moles will have 8 C double bond O, and the energy that will be released will be equal to 8 multiplied by the energy released in formation of 1 C double bond O, and there are 5 moles of H2O. Each H2 have 2 OH bonds, so the energy released will be 5 into 2 into energy of 1 O single bond H. After substituting all the values that are provided in the question, we will get the energy that will be released as 11,032 kilojoule. Finally, the overall enthalpy of the reaction will be energy of reactants minus the energy of the products. So that will come out to be minus 2645 kilojoule per mole.